Good morning, everyone. Welcome back. If you haven't noticed already, the midterms have been returned. Midterm 3 has been returned through CrowdMark, so you can have a look at it. Solutions are posted. They're posted in the assignments part of the Canvas container. So just look at the midterm heading and you'll see the solutions just where they're usually posted. Have a look. If you have any questions, first have a look at the solutions and then feel free to visit the workshop and speak with the TA. I will send a little bit more information out about how to interpret your score, like I usually do, rough letter grades, etc. I won't do it in class today just because we've got to get back on track. So we've got some topics we got to get through. So I will reserve that for an announcement with those further details. Average was 65, median was 70. So those were out of 100%. So yeah, average was 65, median was 70. So the median was quite good. Average is fairly decent. We did a bit of a dip from previous midterm, but in some sense that is to be expected. The material was getting to be a little bit more challenging as it continues to do so. But what the TAs and the graders in general, their main comment was that it looks like everyone is working hard. So that is really nice to see. So the solutions that were presented, the way you were articulating, what it was you were doing, those all looked like everyone was working quite hard in the course, which is really nice to see. So with hard work will come rewards. So we'll see that on the final exam, hopefully. All right, let's have a look at where we are. So we're in the section 15.5 surface area. We'll do a couple of examples and then we're going to be moving on to section 14.8 Lagrange multiplier. So that's coming back to optimization, but seeing a different approach to optimization with constraints. So that's today's topic, surface area. Do a couple of examples to wrap off that lecture and then do a couple of examples from Lagrange multipliers. So this was our integral that represents the area of a surface. So this is a surface given by an explicit function, f of x and y. So f of x, z equals f of x, y. And to find the area, we integrate over the square root of 1 plus fx squared plus fy squared. So these partial derivatives. And there was an indication of where this was coming from. We chop up our surface into a bunch of little bits. That's the first picture. Each of those little bits, it is curvy, but if we cut them up small enough, we can approximate them by straight things. In other words, the tangent planes. The tangent planes, we can get two vectors that make up that tangent plane, that little tangent plane patch, if you will. So there's a little parallelogram patch. We have the two vectors that make up the two sides. They're given by the partial derivatives and the changes in x and y. We take the cross product of those two, and that gives us the area of the patch. And once we have the area of the patch, then we can integrate over all of those patches. And so that's why we're getting the integral of the square root of this expression involving the partial derivatives, because that was coming from these little parallelogram patches that we use to approximate the surface. So let's go ahead and do an example. Let's find the area of the surface. In this example, in the first example, part A, it's going to be part of this surface, z equals xy, that lies within the cylinder, x squared plus y squared equals 1. So let's get an idea for what this looks like. It's going to be a hyperbolic paraboloid, but it's going to be slightly rotated. So it's going to look something like this. So it's a saddle-shaped region that kind of looks like, high back. Maybe I'll put this in a different color. Sort of high back, coming down, and this is sort of where the legs would hang down on that sort of saddle-shaped portion. And let me fix this part of it. It's going to sort of come down. And this is going to be just on the other side. So maybe something like this. And then we've got some sort of lower portion to it. So I'll sort of sketch some lines in here to see what we get, what it looks like. So maybe some things like this, some sort of lines that indicate how this thing is looking. So it's like a saddle that there's a high front and a high back. And the other portion sort of drop down. The legs kind of drop down beside. And it's opening along essentially this curve like y equals negative x or y equals x. So it's not opening along the axis, so it's slightly rotated a little bit. So that's what our surface kind of looks like. And what we want to do is we want to find the area of the surface that lies within the cylinder. So, in some sense, we don't need the sketch for this. We just have an expression that tells us how to compute the surface area. But let's go ahead and do the details that expression is telling us. That expression is telling us we need to do. So we've got our function f of x, y. What we're going to need for this function is the two partial derivatives, the x partial and the y partial. So the x partial is y and the y partial is x. And then to get the area of the surface, we are going to integrate over the particular region that we're interested in of the square root of 1 plus the x derivative squared plus the y partial or the y derivative squared dA. So there's our integral. We need to figure out what is that region D that we're integrating over. So we're supposed to be integrating this thing over the cylinder because we want the part that's inside that cylinder. So we'll get a little sketch here of what our footprint of our region of integration is. So it's a cylinder, radius 1. So in the plane, it's going to be this disk of radius 1. So this is x squared plus y squared is equal to 1. And the thing to keep in mind here is that we're integrating over a disk, so we're free to choose our coordinate systems however we want. So we're going to switch to polar coordinates, and that's x equals r cos theta, y is equal to r sine theta. Okay, and so we're going to go for theta from 0 all the way around to 2 pi and r from 0 out to 1. I'm not what's the question are we on? I think maybe someone might be having sound issues is what. Oh, what section are we on? Or surface area. Where we have left off last day, section 15.5. So we're going to integrate from 0 to 2 pi and from 0 to 1. So that's our theta value and our r value. And since we've switched to polar, it's going to be a 1 plus r squared. And then the area element is r dr d theta. And so this is the integral that we're going to want to evaluate. The nice thing is we've got this r out front. It might help to visualize it if it's just sitting in front of the square root sign. So a substitution can work. So we could do a substitution here, and that's not a problem. So I will leave the details of the integral for you to work out. I will just fill in the final result. That's 2 pi by 3, 2 to the 3/2 minus 1. So this is a substitution at this point. So it's really about the setup of the integral. All right, let's have a look at the next example. So we want to find the surface area of the part of the sphere is given here, that lies inside the paraboloid. So we've got a sphere, and it's going to be the portion inside the paraboloid. So if I look at this paraboloid, I see that's the paraboloid opening along the y-axis. So it's going to be opening like this, and we'll fill in how much more we have to consider in a second. Maybe I'll make it a little bit wider. Normal paraboloid sort of opens a little bit wider like this, because I have to fit a sphere inside there. So then we've got a sphere that actually will, it's probably going to be more helpful to draw the sphere first to see how our paraboloid sits. So we're going to draw the sphere first. So what is our sphere? We've got x squared plus y squared plus z squared is equal to 4y. So we'll complete the square to figure out where the center of our sphere is. So bring a minus 4y plus a z squared is equal to 0. So it's the square on the y that I'm going to complete. That's a y minus 2 all squared plus z squared. When I completed that square on the y by writing it as a perfect square, y minus 2 all squared, what I've done is I've introduced an extra factor of 4, namely that negative 2 squared on the left side. So I've got to balance it by introducing that same factor of 4 on the right side. So there's our equation of our sphere. It means its radius 2, so its center is going to be at 0, 2, 0, and its radius is 2. So it's centered at a y value of 2, and its radius is 2. So there's our sphere. And that's a value of 2. And then we've got our paraboloid that we're going to have to draw, and it's going to cut out a portion of the sphere that sits inside it. So let's figure out where they intersect. What is our intersection of our sphere and our paraboloid? So we've got x squared plus y squared plus z squared is 4y. That is our sphere. When we look for the intersection with the paraboloid, I see that this x squared plus z squared, that's equal to y, because that's what the set of points on the paraboloid satisfy. X squared plus y squared equals y. So this becomes y squared plus y is equal to 4y, or in other words, y squared minus 3y is equal to 0, which is y minus 3 equal to 0, or in other words, y is equal to 0 or 3. So those are the two intersection places. One intersection happens when y equals 0. That's basically going to be the origin. They both pass through the origin. The other intersection is when y is equal to 3. So that's out here. So there's our y equals 3. And so that means we're going to get this intersection happening at these points here. So when I draw my paraboloid, it's going to pass through those points. And it's also going to carve out, because it's three-dimensional, it's going to carve out this circle on the sphere. And it's this circle together with all of this stuff on the sphere. So that sort of cap of the sphere, that right-hand cap of the sphere, is what we're interested in. So this is what we're interested in the surface area of, is this cap. So this cap is what we're trying to find the surface area of. Okay, so let's have a look at the region we're integrating over. That's now our function. Our function is going to be the set of all these y values that live on the sphere. And we are going to integrate over a region in the xz plane, basically the footprint of this cap as projected onto the xz plane. And that, again, is going to be a disk. And it's the disk that we get by projecting that cap, or that circular cap boundary, down onto the plane. So this is a disk of radius. Well, what is the radius of this cap? We know the y value that, that we have. And so what do we get? We get, let's see here, the intersection is going to happen when y is equal to 3. So what we get is, we can look at our paraboloid here. That's our intersection. When y is equal to 3, that's the disk that we're getting. So this is x squared plus z squared is equal to 3. And so we can go to polar again. We'll go to polar coordinates. And our r value is going to sweep out from 0 to root 3. And our theta value is going to go from 0 to 2 pi. I'm just checking the chats now. So the question looks like about the 4. So when I square this side, let's see, when I square out this side, I get a y squared minus 4y plus 4. And so I've just introduced a plus 4 on the left-hand side of the equation. So I got to balance it by adding a plus 4 on the right-hand side of the equation. All right, so let's have a look at our integral now. The integral is going to be the area of this surface. It's going to be the integral over the region D of the square root of, and what do we get? So we're going to have to integrate a function. What function are we integrating? It's going to be a function f of xz, or y values are equal to f of xz. And it's the portion of the sphere that we're interested in, the spherical cap. So that's going to be the square root of, well, let's focus on one of these equations to help us out with this. So I will actually draw it in up here. Okay, so this is, we can write down our equation of x squared. I'll use the completed the square version. X squared plus y minus 2 all squared plus z squared is equal to 4. And so solving for y, we get y minus 2 all squared is equal to 4 minus x squared minus z squared. And then we have to square root it to be able to get access to that y. So that's 4 minus x squared minus z squared. And then the 2 moves over as a plus 2. So that's the representation for that right-hand hemisphere, in particular that cap. And so that's the function we're interested in. Z squared plus 2. So that's the function we're interested in when we're doing our integral. I'll move it down a little bit just to get it out of the way of the rest of the calculations. All right, so what we need now is our x and y partials. So maybe I'll just jot these down. We've got our x partial. We're going to have to use get our y partial as well. And so our x partial is going to be taking the derivative of this. The 2 is a constant, so it differentiates to 0. The square root, we get the square root on the bottom now. 4 minus x squared minus z squared. I get a half out front when I take the derivative of that square root, but that half's going to cancel with the 2 I get when I take the derivative of the inside part, that negative 2x. So what I get is a negative x as a result on top. And similarly for the y, 4 minus x squared minus z squared. And so there's our two partials. And that's the thing we're going to be plugging into our integrand. So we've got a negative x over the square root of x squared. Sorry, I'll fill in the stuff under that square root sign. It involves a 4 minus x squared minus z squared, all squared. And then a negative y square root of 4 minus x squared minus z squared, all squared. And that's going to be an integral, an area integral, so with respect to dA. So there's our integrand. We can do a little...
Oh, sorry, Jim, you mean after that? For the
oh, yeah. Z, thank you. Yeah, force a habit going for the two variables thinking they are y variables. Yeah, they're the z variables. Thank you. And this one up here as well. Z, I'll put it in a different color. So these are the corrections. Z, yeah, thank you very much. And so then our integrand becomes, so we're going to get an x squared. We're going to get a z squared. We're going to get that common denominator of a 4 minus x squared minus z squared, because they're both being squared. And then I'm going to put the 1 over that same common denominator as well. So that's a 4 minus x squared minus z squared. So that's squaring both sides, squaring both of those pieces, realizing the common denominator is 4 minus x squared minus z squared. So putting everything over that common denominator, we get a whole bunch of cancellations that happen. And so our integral then becomes the integral of over d of 2 over the square root of 4 minus x squared minus z squared dA. So that's our integral now. We've now going to switch. So we're going to do a change of variables to polar. And so then it becomes the integral from 0 to 2 pi, the integral from 0 to root 3, 2 over the square root of 4 minus r squared, r dr d theta. And again, with this change of coordinates, now we have an r sitting outside of this square root, so perfect for a substitution. So a substitution for what's under the square root of 4 minus r squared. So again, at this point, it's just details of the integration. And I'll write down the final result. Ends up being 4 pi in this case. All right, so there's the details. In this case, we had to change our perspective and look at y as a function of x and z, but everything follows through as usual. We're just now integrating. We're integrating in a boundary in the xz plane of particular y values. All right, so this was a result that wasn't, in some sense, really a surprise. We saw methods for computing surface areas of solids of revolution back in Calculus 2, but this now is saying that, you know, all of these results that we had for surface areas of solids of revolution in Calculus 2, now we've extended to Calculus 3. We just have it now a general method for finding surface areas, which encompasses all of the previous methods involving surfaces of revolution, but also involves other surfaces that aren't of revolution as well. And so we now got a general method. We integrate that square root of 1 plus the x partial squared plus the y partial squared. So we'll look at one more example. Let's figure out what the area of the part of the plane So there's a plane given with a normal vector that's made up of some parameters, A's and B's, etc. And so we want to find the area of the surface, area of a region in this plane that projects down to a region D in the XY plane. And if we know the region in the XY plane, so if we know the area of its shadow, can we find the area of the region itself? So we'll just get a arbitrary sketch here. We've got a plane. We've got some region in the plane that we'd like to find the area of. So this is going to be our surface S. It projects down to some region D in the XY plane. And we want to figure out what the relationship is between these two areas. So the idea is we know this area down here. We'd like to find the area of the region up here. And if you're looking at it and your immediate thought is they look like they're the same, then just try to think of, something like this, taking that plane. And if that plane was flat, then I completely agree. Whatever region's drawn on the plane, it's going to be the same area as the region down below. But as soon as you start to tilt that plane, then the shadow projected down below starts to get smaller and smaller. If this plane is almost vertical, then the shadow that little area section projects down below is tiny, very tiny down here. So that's the thing you want to keep in mind, is that the relationship between these two areas should be related to the normal vector to that plane. And that's what we're finding in this formula, is that it actually is related to the normal vector in this plane. So let's get a feel for what this integral is going to give us. So we're looking at this plane. That's going to be our function. So f of xy is equal to ax plus by plus c. We're going to get its x partial, that's a. Its y partial, that's b. So then what is the area of S? The area of S is the integral over that region D of the square root of 1 plus the x partial squared plus the y partial squared dA. So that's our surface area formula. The integrand is now a constant, so we can bring it out. That's a 1 plus a squared plus b squared. And so then that's multiplied by the integral over this region D of 1 dA. But the integral over this region D, with respect to area, that's just the area of the region D. So that's a 1 plus a squared plus b squared area of D. And so that's what we wanted to show. So we've proven the result we wanted to show. Now I alluded to the fact that it seems to be connected to the normal vector. So let's just get a feel for what the normal vector is. This is a plane. We could write it as ax plus by minus z is equal to negative c. So I'll just switch where the positions of z and the constant are. And so now I can think of this as a level surface of this function g of x, y, z equal to ax plus by plus or minus z. So this is a level surface of ax plus by minus z. And so the normal to this surface is given by the gradient. And that's the normal to this surface. So in other words, the normal to the plane we're going to get as this gradient. There's a few ways you can do this, but this is one way. Just recognize it as a level surface, and therefore the gradient's the normal. So our normal is going to be a, b, negative 1. So there's our normal to the surface. So that means if I pick a point on here, then the normal vector is going to be that gradient of g, which is a, b, negative 1. And we see that this is just now the gradient, the length of the gradient to that surface times AD. So that's really what that formula is saying, is that the area of that surface on, the area of the region on the surface is related to the area of its projection by the normal vector to the curve, in other words, or the surface, in other words, the gradient. So this is the relationship we get there. So that was what I alluded to when I said it all depends on how sort of steep the plane is tilted in relation to the plane that it's projecting onto. And that's this connection now with the normal vector. All right, so that's it for the surface area section. This is one of the reasons why I pushed it off until after the other stuff, is because it's really just a particular integral that represents surface area. So it's really just another bunch of exercises in integration. The setup isn't that challenging in this one either. So the triple integrals and the double integrals in our setups were really the more challenging thing. With this one, with surface area, it's just, here it is. There's our surface area formula, and we just go ahead and apply it. All right, so the next thing I wanted to do is to get to Lagrange multipliers. So this is 14.8. So Lagrange multipliers, we're coming back to chapter 14. This is the only section we've skipped in chapter 14. The reason I skipped it initially and am now coming back to it is for the following reason. So I'm going to jump back to 14.7 for a second. 14.7 was our max-min problems. We learned techniques for finding critical points, and then once we found critical points, we classified the critical points. Then we worked on some examples of optimizing functions. And then we did an example like this, very similar to the one we had on the midterm as well, ones you worked on the homework assignment. So we got a wooden box without a lid, is to have a volume of 32 meters cubed. Find the dimensions that minimize the amount of wood used. So the idea here is that there's three variables, X, Y, and Z. But our techniques we have are optimization techniques for two variable functions. So functions of X and Y, let's say. And so we find the partials, set them to 0, get the critical points, etc. This one is three variables. But we can convert it to two variables by eliminating one of the variables using this constraint that we had. We had a constraint on the variables here. We had that X, Y times Z had to equal a fixed volume. So we use those to isolate one of the variables in terms of the other, so Z in terms of X and Y. And then in our surface area formula, which we are trying to minimize, we replaced Z with that expression in terms of X and Y. And so we reduced it now down to two variables. And then we can go ahead and do our two variable optimization techniques. Now, it turns out that if we're a little bit clever in how we look at the geometry of the situation, we can avoid having to eliminate one of these variables. And in this case, avoid having to go with fractions or ratios because the X and Y's are on the bottom, and then avoid having to deal with some potentially tedious calculations. And that's what this next section's about. This next section, Lagrange multipliers, is coming back to some of these problems that we dealt with in one way. Whoops, wrong section. And then dealing with them in a different way. So this time machine was essentially just that one I just looked at. So I'm not going to really write down anything here other than just that we eliminated Z variable in terms of X and Y, and then that reduced to a two variable max-min problem. Okay, so this is where the word time machine is coming back. It's really just saying in the previous lecture, lecture 14.7, this is what we would have done for a problem like this. However, we can do it in a different way. So what we're going to observe is the following. So just look at the picture for right now. And the function f is, I've reduced the dimension here. So we're just going to focus on, this would be a 2-variable one that we could drop down to a single variable or a calculus 1 type problem. But typically we are interested in more than 2 variables, 3 or more variables. And so that's where, well, in this case, it's 3 variables. So that's where the expression up above has more dimensions than the picture, but the picture will help us to sort of figure this thing out. So what this says is, I'm interested in figuring out the maximum value f has if I allow the inputs to only satisfy the condition given by g. So in other words, if I'm looking at the picture down below, what's the maximum value f can have if my inputs x and y are only allowed to live on that blue curve? So what are what's my maximum value f can have if my inputs just live on the blue curve? So I imagine just picking points on this blue curve. What are my f values at these points? You know, if I'm standing right here, my f value is 7. So this is a point where f is 7. If I move over here, I can read off the level curve. This is f is 8. What's in between those if I picked a point here? Well, that's at a point between those 2 level curves. So that's probably f is somewhere around 7.5 or something like that. So we can start to read our z value information off of this picture. And so as I continue along, I see that my f values are increasing, and then I get to a point here where the f value is 10, and then they start to decrease again. So I can see from this picture that the maximum value f has, if I only restrict my inputs to come from this blue curve, the maximum value f has is 10. Exactly, perfect, thanks. Thanks for that in the chat. So that's not the whole story I want to get from this picture. What I want to get from this picture is the relationship between the blue curves and the red level curves. What's going on at that point 10? Or in other words, what's not going on at the other points? So pick any other point. I'll pick another point, let's say down here. I know that at this point, let me put it in pink. I know that at this point here, that f can't have a maximum there. Why not? Well, because I'm standing on a level curve and my blue curve has values on either side. So a value over here is going to be higher, whereas a value over here is going to be lower because I'm on the lower side of the level curve at that point, or I'm on the higher side. So I know at that pink point, if I move, because I'm traveling across the level curve, I'm going from, if I'm traveling, let's say I'm traveling down in this direction, then I'm going from high values to low values. I'm actually descending down the slopes of this surface. And so I know it can't be a maximum there or a minimum. I can't have an extreme point there. The reason I'm getting an extreme point at 10 is because my level curve is tangent to the blue curve. So the blue curve and my level curve are tangent to each other. So there's a point of tangency there. And because they're tangent, it means that the normal vector to one curve, the normal vector to the blue curve, that would be grad g, and the normal vector to the level curves f, which is grad f, are parallel. They got to be parallel to each other. If the curves are tangent, their normals are parallel. So if the curves are tangent, their normals are parallel, and those are their normals. And so that's what this statement is saying up here, saying that where will you find a maximum and minimum of f, given that you've restricted your inputs to the constraint g? You will find them at the places where the normals are parallel, where the gradient of f is some lambda times the gradient of g. So lambda is just this parameter that's telling me that they can be scaled, but this is just one's a linear combination of the other, or one's a multiple of the other, and lambda is that multiple, which we call the Lagrange multiplier. So let's see how we can actually use this in practice. So this is the main idea. You got a function f, you're trying to optimize, and you're constrained. X, Y, Z have to live on this curve g of x, y, z equals k. Then, yep.
So can we go back for a minute?
Sure.
About the normals.
Yeah.
When you say that they're parallel, so in this image, though, they're actually collinear, correctly? Is that correct?
So parallel and collinear. So what do you mean by collinear?
Well, like the normal off of the blue line would.
Let's draw that one in here. Normal off of the blue line. Yep.
And then the normal off of the pink line would be like they're kind of in the same line.
Yep, that's what it means to be parallel.
Okay, so when you say parallel, that means that they're not always collinear. They could actually be just parallel to each other.
Well, I mean, collinear and parallel, do they not mean the same thing?
Do they mean the same thing?
Yeah, parallel just means that, you know, V and W are parallel, means that these are vectors. So V is some multiple of W.
Okay.
Collinear is usually a term that's, you know, it's usually a term that is in reference to points. So 3 points are collinear if they live on the same line.
Oh.
And so parallel is really the corresponding concept for vectors. Vectors are parallel if one's a multiple of the other.
Okay.
Does that make sense?
Yep.
Okay.
Thank you.
You're welcome. So there's our technique. Is what we have to do is we have to solve these equations. These are just the unpacking of the equation. The gradient of f is equal to lambda times the gradient of g. So where can the maximum and minimum occur? They're going to occur at points x, y, and z where the gradients are parallel to each other. The gradient of your constraint curve and the gradient of your function are parallel to each other. And they also have to live on the constraint curve. So they have to be in the domain that you're restricting your attention to, and they have to satisfy this gradient condition. So let's go ahead and do an example. We'll do this tank example, which we are so familiar with from our previous techniques of finding optimization, optimal points on surfaces. So let's get a feel for what our cost function is. This is the thing we're interested in maximizing or minimizing. So I'll put some variables in our picture. X, Y, and Z are these respective dimensions. And what is going to be our cost? So we're only interested in the base of the aquarium and the sides, not the top. So what our cost is, it's going to depend on X, Y, and Z. The base is 5 times as much as the glass. So our base is going to be 5 times, let's say its area. Let's say that cost is whatever the cost is per unit area. So this would be 5 times the unit area of the bottom. And then we've got 2 sides that are of dimensions y, z. That's basically the left and the right. And then we have our front and back, which is our 2x, z. So there's our cost function. What is our constraint? Well, our constraint is that we need a volume of fixed value v. So our constraint is that v is equal to x, y, z. Or in other words, g of x, y, z, which is our constraint function, is x, y, z minus v. So we've got our cost function, and we have our constraint. In particular, we're interested in when this constraint is 0. That's our level surface where these inputs are coming from, where g is equal to 0. So there's our function g. The method of Lagrange multiplier says, look for the points where the gradient of c is a multiple of the gradient of g. And so we're going to split this up, and I always like to just unpack it as all the equations. So cx has to be lambda gx. And then we get another equation, cy has to be lambda gy. And we get another equation, cz is equal to lambda gz. And we have our constraint equation, x, y, z is equal to v. So we are trying to solve all 4 of these equations in 4 unknowns. So we have 4 equations in 4 unknowns. Make that a little bit clearer. 4 equations, 4 unknowns. And they're not linear equations either. But these are the 4 equations we're going to try to simultaneously solve. So what is c sub x? C sub x is the x partial of the cost function. That's 5y plus 2z is equal to lambda, and then the x derivative of g, which is yz. Cy is 5x plus 2z is equal to lambda times the y derivative of the g function, which is xz. And cz is 2y plus 2x is equal to lambda times xy. And then we have our equation xyz equals v. And of course, just a reminder, v is a constant. It's not a parameter, it's not a variable, it's not something we're allowing to change. It's the fixed volume that we want our tank to have, whatever that is. So what are our 4 unknown, or 4 equations? Sorry, 4 equations are obvious. What are our 4 unknowns? X, y, z, and the Lagrange multiplier lambda. So we want to solve these equations. And this is where the fun begins. Now we're just into the realm of algebra. So we need to solve these equations. We don't have a general technique that will work. If there were 4 linear equations in 4 unknowns, then we'd use linear algebra, techniques from linear algebra, augmented matrix, row reductions, and the like. But these aren't linear equations. And so we just have to use ad hoc techniques. And so with all of these Lagrange multiplier problems, it's always about just doing the best you can, trying to figure out how to solve these equations. So I'll show you how we can do this particular case. What I notice is that there's a lambda yz, lambda xz, lambda xy in the first 3 equations. If I add extra variables to each equation, I can turn those right-hand sides into the exact same thing. So I'll take that first equation and I'll multiply by x. Actually, what I'll do is I'll do it up here. I'll do it inside. So I just moved the equation up. Sorry, I know you don't have the ability sometimes to move if you're writing on paper. But what I've done is I've just taken that first equation and just scaled it through by x. And I'll do the same thing for the next one with respect to y. Scale through by y. 2yz equals lambda xyz. And do the same thing for the last one. Scale through by z. Xz is equal to lambda xyz. And the reason we've done that is because now they all have the same right-hand side. So in one, what I'll do is I will take this one and set them equal to each other. So I get 5xy plus 2xz is equal to 5xy plus 2yz. And the 5xy's cancel. I get the 2's canceling. And so I get the equation xz is equal to yz. So that simplifies down quite nicely. That tells me that there are two solutions. There's either going to be a z equals 0 or an x equals y solution. Can z equal 0? Well, no. If z was 0, it wouldn't satisfy the constraint. In other words, we need a volume of v, and if one of the dimensions was 0, our volume would be 0. Constraint not satisfied. So x must be equal to y. And I'll do the same thing for the next one. What I'll do is I'll take, let's say, equations, let's say the next two. So the y equation, the second equation and the third one. So let me draw a couple of different colored arrows here. So this one and this one are going to come down. And I get, those have to be equal to each other. So 5xy plus 2yz is equal to 2yz plus 2xz. And I get the 2yz's cancel. So I get that 5xy is equal to 2xz. And so I get, again, either x is 0, which can't happen because the constraint wouldn't be satisfied, or 5y is equal to 2z. Or in other words, z is equal to 5/2 y, which is also 5/2 x, because x is equal to y. So I get that expression as well. And so I'm doing pretty good. I've got x is equal to y, z is also equal to 5/2 y. So both my variables, y and z, can be written in terms of x. And now we plug into the constraint. So I'll actually do that underneath the constraint section. So now I take these two things and I just plug them in there. And I get that x times y, which is also equal to x. So that's an x squared, times z, which is 5/2 x. Oh, okay, so things are boiling down quite nicely, because that becomes a 5/2 x cubed is equal to v. Or in other words, x is equal to the cubed root of 2/5 v. And so there we go. We found our point. X is equal to the cubed root of 2/5 v. Y is also equal to the cubed root of 2/5 v. And z is equal to 5/2 of the cubed root of 2/5 v. And we could, simplify that last one, because there's 5/2 and 2/5 under the cube root, but I'll leave it like that. And so what we've done is we found our dimensions. So these are the dimensions that will minimize the cost of the tank. You may wonder, how do you know it's a minimum? We didn't actually do that. So this is minimum cost, minimum because of the nature of the problem. What do I mean by that? I mean, if I'm looking at the tank and I look at my cost function, if I take x and z, let's say, or even x and y, let's say x and y, because that's the base, and I just make the product of x and y as big as I want, then that makes the base as big as I want and drives the cost up, because that's the first factor in the cost function, 5 times xy. So I can make xy as big as I want and drive the cost really high. How do I know that I can still make a tank? Well, the constraint just tells me that z has to be v over xy. So z is going to be really small. So it's going to be a tank that's got a really wide base, but is really short in height. Those exist. Those are at the extreme of the ones I want, but those are ones with really high cost. So I know that the critical point that I find has to be a minimum, because I can make the cost as high as I want. So this has got to be a minimum cost. That's why I've referred to it as the nature of the problem. This is going to be a minimum. I don't really need to check that. All right, so that's our Lagrange multipliers. I didn't intend to do all the examples today. I wanted to give you one example in class that really illustrated everything. The other examples I will do, I'll just do them as videos, and I'll post them as separate videos, each of them just in their own little video, so you can go and refer to them later on as you're working on the homework assignments. So that's it for today. That's it for the Lagrange multipliers. So I'm going to stop the recording.